Hello, guys. Yes, I think it's about time to start. And it was amazing, the first part. I was really, really excited about. I think all the right people were there to talk about they were very well chosen, very well curated. And now we are having breakout sessions. And the first one will be about biohacking in space. So I would like to actually open the mic for you to introduce yourself, Nicolas, and tell us about a little bit about your work and about where are you are from, and everything that you would like to share in the introduction.
Okay, so yeah, hi everyone. Thanks for having us in the session, especially to you, Isis and Chad and David, because of the accommodation last minute thing. And so the name of the session is Why on Earth Go to Space and How? So basically we are going to be answering these two questions. Why is relevant space for biology? And also like how to send something to space, or what to do, what is the timeline, budget, anything that it's a barrier for you for sending something. So we can answer that questions. So for this panel, we have Molly, Karen, and Hilde. Molly is right here, right? Yes. And she is a payload developer for NASA projects and also for the International Space Station. And she has experience sending biological experiments into space and with open innovation competitions, some experience also in Israel. She has a PhD in mechanical engineering. Karen, I think you already know her. She's a
Some
PhD.
people know me, not everybody.
Okay.
Though I am extroverted, so maybe by the end of this, I'll know everybody in the global bio community.
Okay, so I introduce yourself. She's a PhD in ecology and evolutionary biology from University of Pennsylvania. She's the CEO of Biorealize, and they have very cool portable incubators, which she has just like there. And so we are within Ice Cubes. We are collaborating also with them to bring those incubators to space. And finally, we have Hilde, that she's working also with Ice Cubes, and she has experience in science coordination for the International Space Station for more than a decade, and now is helping researchers and students find a way to send their biological experiments to space. So
good afternoon.
Okay, sorry. So as for the structure of the session, I will briefly introduce myself, and then I will tell why are we here and why are we talking about space, and then we will go through the panel, and then we will have a very short Q&A. So put your questions in the chat. So I participated in the IGEM 2018, and by that time I was working in the European Astronaut Center. I was doing some bacteria consortia for recycling astronauts' urine for having something to eat out of your urine. So and in there. In the IGEM, I was looking into different groups that were working with space, and I thought, why don't we create like a community or some kind of initiative that unites all of the different all this synthetic biology in space, just for having more visibility, having more power because of the community. So I started that international community, and I was about to create an international workshop in London with experts. I was about to secure some funding also from Germany and Denmark. And I was also, as I told you before, I was invited by John Converse to Beta Space. That is a California event that is focused in sustainable settlement of space using synthetic biology and technology. And after all of these efforts and all of these activities, I realized that actually the network and the community in synthetic biology in space, it was actually something that it was existing. But the thing is that it was very reduced, and the thing is that not a lot of non-space sector was included in the discussion about space. So we thought that this was a very interesting opportunity to share with you that space is kind of open. We want to improve the accessibility to it, the diversity to it, the people that can join. So we would like to inspire you so you can think about your ideas in space. So going straight to the panel, why is space important for biological research? Hilde, for example.
Sure. So the environment that we find, for example, on the International Space Station has a number of unique assets that you can actually not reproduce on Earth. And it has effect in terms of biology at all levels. And so there has been, as you mentioned also, there has been quite some research done over the last decades that allow to establish a number of these effects. And now is a very exciting time, I think, also in the way you phrase it, that space is opening up for possible utilization of these results of the past. And so on your question, so why is space important for biological research? So you can actually do biology or reach biological effects that you cannot have on Earth, like, for example, cells that form more easily three-dimensional structures without the need to scaffold or to matrix, and you can do so because of the effect of microgravity, so a lack of gravity or very small gravity, and so you can create better 3D cell culture models. Also, you can do very interesting things with stem cells. People would say that stem cells show a kind of enhanced stemness, so it makes it interesting actually to use stem cells in a space environment. In general, you see changes in gene expression and many other effects that have actually been observed, let's say, but that now can be exploited, I would say, for scopes that either address how we can prepare for space exploration, but also that we can utilize these assets for research and development activities that is relevant for us here on Earth, and maybe could even lead to manufacturing of items or biological items that are relevant for us here on Earth.
And which are the platforms that can allow this, the benefits you are talking about, which are the platforms that can allow this to happen? So which are the platforms that can expose your biological things to space?
Yeah, so there's different platforms, and if you mean platforms in terms of where you can go in space, so in fact there's different type of facilities or platform that you can use. Even here on Earth, you can actually have some type of microgravity by going, for example, into a drop tower, but it's only a couple of seconds, or to go to a parabolic flight, so a plane that makes parabolas, and during 20 seconds or so, you get a relatively good, microgravity. If you need microgravity on a sustained duration, so longer duration, then the International Space Station is your best platform, I think. There's also CubeSats, for example, although I think CubeSats, these are these small satellites in the form of cubes. I think for biology it might be a bit less relevant, although they're very cute and very exciting. So I think in the end, there's a lot going on the International Space Station in terms of biology based on space assets. And then for sure there will be future space stations or free flyers that can be very relevant as well. And inside of the space station, you then again have different type of facilities, kind of lab facilities or racks, as we call them, that can be used also for different type of biological purposes.
And Molly, I would like to hear a little bit also, like, why do you think that space is important? And also if you can maybe also differentiate between the different platforms, what can offer.
Definitely. And also I noticed in the chat, people are asking how to send samples to space. So I'll address that too. So Hilde did a great job talking about all the platforms from the ISS to satellites. And those are the two that actually live in what we call low Earth orbit, or LEO, which is 250 miles above our head. It's really not that far when you think about it. I'm sure most of us have traveled that far in the not too distant past. So it's the place where I always like to say that's where astronauts are hanging out. It's been continuously inhabited by astronauts doing research since 2001. So it's exciting, and it's where the shuttles used to hang out. It's where we've done most of our research in space, both for going out to explore space, but also for benefit back on Earth. So if you want to get to true microgravity, this is where we can achieve it, is in low Earth orbit at this point, for things that you want to bring back to Earth easily. But you can also use various platforms that give you either a small amount of give you microgravity for a small amount of time, or simulate microgravity. So it's not as high quality is the best word to say, because we're talking about when you're in low Earth orbit, you're at about 10 to the -6 G, versus simulators give you things that are more in the area of 10 to the -2 G. And you do have to stop them and check your samples, which then exposes them to gravity. So we have simulators that you can rent or buy and use in your desktop in your lab. We also have, as Hilde said, balloons, and we also have, like, people might have heard of it, might not, but the Vomit Comet. It's the airplanes that make big parabolas. So you go from microgravity, or 0 G, if you will, all the way to hypergravity 2 G during about a minute of flight. And they do that, I don't know, somewhere between 40 and 60 times, depending on weather and which plane you're using. And then there are balloons and drop towers, and all of these things offer you a way to start testing your projects before actually going to space, if that's your ultimate goal. And so I know you asked one other question, Nicolas, and I got myself a little sidetracked. I had to close the chat here because it was distracting me. But I just want to address quickly getting samples to space, because it is really important. How do you actually do research? How do you actually go to space? There are a number of avenues. There's the traditional avenues of using NASA or the European Space Agency or the Japanese Space Agency and flying from your home country or your home space agency and going through one of their grants or programs that they offer. You can apply to fly your samples. And then in the US, we also have the ISS National Lab, which is a bit different than other national labs, but it's still a national lab nonetheless, and they sponsor programs themselves. They have open innovation competitions, and they also work with both the NIH and the NSF to do sponsored research every year that you can apply to.
So as for these opportunities, imagine that I'm I don't know, a student, a association, a community manager, a teacher. Like I find it kind of hard to figure it out how to go from the idea of, okay, it would be great to send something, to actually, you know, like talking or expressing some kind of detailed or some kind of minimally detailed proposal or to someone. So how do you do that?
So there's a lot of ways, but the most important thing is the ISS National Lab offers a lot of workshops and sessions where they talk about this. And you can become a space expert to whatever degree you want, but there's always someone, whether it's someone at the National Lab or someone like me or Hilde, who you can talk to And again, there's a lot of workshops that go on. There are different conferences that go on, just so you can come and start learning and hearing about it. And I know all of us try and frequently go to conferences to start to get the idea out, because it is not the easiest idea to wrap your head around of why I would go to space to benefit what I'm doing on Earth. But I'm going to share one story about this. I worked with a pharmaceutical company who may or may not have heard of, but Merck, and we worked on their drug Keytruda to find a better way to create a better form of the crystal, because when you don't have gravity, you can get some different shapes of the monoclonal antibody that is Keytruda, and they're actually trying to find a way to stop delivering it in the clinical setting through a port. Instead, they want to be able to put it in something that looks like an insulin pump so people can actually get it at home. And they're using microgravity to try and find a better form of that crystal so that they can deliver it in a home setting and not expose people who are sick to the hospital, and also to try and get the dose down for fewer side effects. So this is one example of how people are actually using space. And Hilde brought up some great examples, but the New York Stem Cell Foundation has also found out a lot of things about stem cells, and that they have more stemness. That's how they always describe it, and that they have better proliferation they see when they're studying them in space. So there are a lot of opportunities, there's a lot of groups, and we're all here to help, and the ISS National Lab is definitely here to help you too and answer any questions you have.
And so that's super interesting. But I think that maybe also like when we talk about the pharma companies, or maybe it's something that is, I know for some people it might be a little bit like out of the scope of their life, kind of.
Mm-hmm.
So could you share some examples, Hilde, about maybe some educational projects or some other, regarding education, for example?
Sure. And I would echo that what Molly said, that if you have an idea and you don't immediately know how to find your way, don't hesitate to reach out to one of us, and we can help you in first iterating your idea, but also in where you could find grants or things like that. So, but for your question, so examples of projects that we have been doing that involved students. So we worked, for example, with the International Space University on a number of cubes. So we work with these cubes that are 10 by 10 by 10 centimeters. I'm sorry for the European centimeters. We had some where we looked at the effect of microgravity and radiation, because also people are making that very relevant comment that you also have the effect of radiation on the space station. And so that investigation looked at plant germination and plant growth, and how microgravity and radiation played into that. But we also had some student project related to more biomining. So how can you use bacteria to potentially produce methane in the future? And how, again, does microgravity and radiation play into that? But we're having others more like artery and microgravity. It's a European Space Agency university competition winner, and it looks at the effect of on blood behavior and arteries under microgravity conditions and under radiation effect. So completely different direction. So I also really like that. And we have some experiments, for example, on probiotic bacteria culturing that could be used in dietary supplements for astronauts. So very, very wide range. Can be microbiological, can be more plants, can be more at the level of cell studies. And I think it's all relatively easily in terms of setup. And maybe you can also address Karen, because she has a very nice setup that I think is also within reach for everybody.
Yeah, so before going to Karen, just like I would like to know also, like, which countries are the ones that you are kind of having into all these educational projects? Is varied or?
Well, this is space, so it's a global endeavor. So in terms of countries, I think this is really an international endeavor, and everybody can find their way to bring their idea and their experiment to space.
Okay, so Karen, would you like to explain a little bit what would be your incubator in space?
Sure. I had a chance to meet Molly back in December when we were still traveling out of Berkeley at an innovation conference related to bioindustrial manufacturing. And at that point, the incubators, which I'll describe in a second, we really were only thinking of them in what I now call terrestrial environments, because since meeting Molly and Hilde, I realized that, you know, this is a technology that actually can solve a lot of problems for space research and space discovery. So I'm sitting in my home lab. You'll see my family is nice enough not to put me in the garage, but I'm just one door away. So I have to make sure I keep it clean here and don't let the organisms out. And then behind me, I have our incubators. And so these incubators are portable. They're about 6 by 6. They can fit right into a drum case. And you can grow plants, animals, mycelium, not animals, sorry, plants, yeast, archaea, bacteria, mycelium, you name it, in these incubators. They're modules, so we can do solid cultivation and liquid cultivation. But the real thing that's cool is that all of our sensors are embedded into the incubators depending on the application you're running. And all of that data gets pushed to you on your phone or on your laptop. So pre-COVID, it wasn't totally obvious to people why we might want to be able to set up an experiment and walk away from it and continue to surveil it, actually be able to interface with that experiment and reprogram it while it's going. Now it's very obvious that we need these remote solutions within biology, but that same remote solution becomes a solution for space. Now you can package your experiment into an incubator. You can potentially put it up on SpaceX and get it back down. And SpaceX did launch successfully on my birthday this year, so I took that as a good sign. And while the experiment is up and running on the ISS, or if you're manufacturing organs, you know, in 10 years in low orbit for individuals, this would become a platform for actually being able to see that data in real time. So that kind of constant communication back and forth with the experiments is something that we're really excited to see and start to maybe push forward into this space frontier.
Okay, so and also like as a company, because you are talking about the implications on the research, the benefits for the research itself having your incubator, but as a company, which are the benefits or which is the value that is added, like which is the value that space add to your company?
Well, if we think about low orbit manufacturing, which isn't actually that far off, Molly can talk about this. This suddenly becomes a model where people can rent incubators to manufacture things in space in free flyers. So we do think about that, you know, as a long-term vision for the company. One of the questions that came up in the chat here is, are these homemade DIY incubators? And no, they're not, though I am part of an NSF grant that Justice Walker is talking about, Learn, Design, Bio, where we do have an open source educational version of these. But our intention is to get these incubators in as many people's hands as possible. So we keep them really low cost for a professional version. People can check it out on the site, but our goal is to engage more designers in the process so that they can start working with biology, reimagine how we make things through biofabrication and start to push that change on the commercial side here on Earth.
Okay, cool.
Yeah.
So, and just like before going to the Q&A, because we have 7 minutes, would you have any advice for startups or companies that would like to go to space? Who would they contact or?
Talk to Molly and Hilde. Yeah. It was very serendipitous that Molly and I met when we ran into each other at the conference, but then I was like a dog without a bone once I realized, you know, hey, there might be a fit. And that kind of conversation brought me in contact with Hilde. It has been fascinating to learn about all of the opportunities that are available on space. You do have to have patience. The funding is, you know, one of the trickier parts, but there's a lot of interest. It captures the imagination. It's just cool to go to space. My kids finally think it's cool what I do. But yeah, these are the two women to try and get in contact with. Their network is really extensive.
And if I may add, Nicolas, before we go to the questions, I think there's still a number of misconceptions out there about space, that it's not very accessible and that it's a niche and maybe not for anybody that has some idea. And I really want to emphasize that actually we have been over the last couple of years taking down a lot of these barriers, and it really becomes accessible and not very complex. And we are there with services like ours, like Ice Cubes, like the support that Molly and Karen are given. These are all a kind of ecosystem of support that is existing for people to have their ideas fly to space. So don't hesitate if you have an idea. I mean, really put your own hurdle down to reach out.
Okay, so also okay, you are saying that is possible to fit all budgets, but how do you find funding or?
Yeah. So, oh, sorry, did I step on someone? No. Okay, so there are different routes. There's competitions, there's student competitions, there's open innovation challenges, there's grants. Molly talked about a number of them, depending on in which continent you are. There's different routes. And so we can also help you in that sense. We can see if there's possibility, if you're a startup, to partner or to collaborate on certain scopes, relying more on private money. So there's different possibilities in that sense also to get your idea financed or collaborate, so that also the financial threshold is not high.
Okay, so we have 4 minutes. Wow, reading questions is really hard.
Well,
I mean,
Nicolas, I picked up on one question that I do want to kind of answer. It was way back a few minutes ago, and you know, someone said that they thought this sounded more like physics than related to biology, and I think the really important thing is this is hard to wrap your head around, because everything we do every single day is dominated by gravity. We have this permanent lens of gravity when we are on planet Earth. And when you go to space and you remove that lens, you're right, you're changing the physics of the system. But that's exactly what makes it interesting, is that when you're changing the physics of the system, you get to see things like cells forming 3D structures without a scaffolding or a matrix. If you 3D print, which there is a 3D bioprinter on the station, if you 3D print tissue on station, it doesn't begin to collapse under its own weight. So you can take the time to strengthen it and return it to Earth where it won't collapse under its own weight. So there's a lot of efforts in creating vascularized tissue in space because it doesn't collapse, and maybe it could be something that we could use towards organ transplant. So removing that lens of gravity allows us to learn something new. There's been some really interesting studies on biofilms looking at antibiotic resistant bacteria. Bacteria become more virulent in space most of the time. There are always exceptions to everything. So they behave totally differently, and we have to ask ourselves, is that because it's a situation driven by diffusion rather than convection and sedimentation being the dominant forces? So removing that lens, changing the physics by going to a microgravity environment just allows us to learn something new about our system that we can apply back to Earth, or maybe we find something that can only be done in space and it's so beneficial to humanity that we start manufacturing it there. So there's a lot of options and open questions right now.
Cool.
It's a good point Molly brings up. When we started talking about our technology, we were discussing the fact that you can do shaking incubation as well as static incubation. And then we realized, well, shaking might not actually be all that important in microgravity. So those kind of like the dominated thinking of gravity is so pervasive that once you remove it and allow people to suspend that disbelief, the creative applications and just the seeking out of knowledge in these spaces is absolutely fascinating.
Okay, so I think that we have been kind of on time. I don't know if I don't know if you want to ask any other question from the public.
There's still maybe one question, whether we expect to see differences in biological functions in LEO versus beyond. So I think we talked about two different effects. One is microgravity that you would find also beyond LEO, whereas radiation will be different depending if you go in deep space. Radiation levels will be even more impacting. So.
And just to touch base in probably the 30 seconds we have on this last question that came up about ethics, legal side. So the International Space Station is international, but there are parts that are designated country by country. So if it's legal in your country and not something that could harm an astronaut, so you can't send Ebola or SARS-CoV-2 or something like that to study, you can do it on the International Space Station, and you can, say, hey, this can only be done by a European astronaut because I'm European or American. And basically it is a collaborative space where a lot of things can be done. And there are coming online options that are free flyers that would allow people to do more things that, especially in terms of viruses, that won't hurt astronauts because they're not present there. So.
Okay, so now chat, yes, we finished. So yeah, the closing remarks. We hope that everyone has kind of get inspired by this talk, and yeah, don't hesitate to contact the panelists if you want to ask more questions.
Thank you, Nicolas. Thank you. Wow, that was incredible. That was so amazing to hear about all those aspects, as in the first one. Yes, please, everybody, if you can salute all the panelists. It was really amazing. And as in the first one, there will be a discussion in the docs, so we can continue there. And a lot of the panelists also shared their emails if you wanted to keep in touch. So let's keep the discussion alive, people. And now I think that we can move to the next panel. And I would like to introduce the next talk will be about qPCR. And the person that will talk about qPCR is Marc Juul. Marc Juul is a biohacker. He biohacks from home. He's working in this qPCR virus diagnostic setup and trying to make a chip. So it's hacking on open hardware for that, with hacking specifically a UV spectrophotometer electronics. So he's also co-founder of Counterculture Labs in Auckland. And I will open the mic to him so he can add any other remarks that he thinks it would be nice to share with you too.
Hi, thanks for that introduction. Welcome to the session. So I am not looking to really, I have something I can present, but I am hoping that we can mostly just talk about what people have been working on and share the different things that people have worked on or what they're hoping to work on related to qPCR. I've seen several projects pop up, and I'm sure there is a bunch of people here working on different things. I will just open it up with what I've been working on here and why I've been working on it. And then maybe we can just have people, if people want to speak, maybe they can just say something in the chat, and then we can go around. I'm sitting here in my little garden yurt that I have temporarily converted to a tiny biohacker space because our counterculture labs, our biohacker space is mostly shut down. So that's been interesting, dealing with a lot of smoke coming in and everything being covered in a fine layer of soot. But nonetheless, when this pandemic started, me and some of the people in the neighborhood, we decided to try to get some qPCR working, see if we can do the CDC protocol at home. And what we came up with is that the easiest thing to do is to buy an old used device that's kind of no one really cares about anymore because it's simply too old, doesn't run on modern computers. So we found these MGA Research old Opticon units, and they're basically just a PCR machine, like a previous model PCR machine that they had, but they slapped an optical unit on top. And you can get them for like $300, $400 on eBay sometimes. And of course, they're a little bit old, they're a little bit slow. They only do 96 wells, but they work, and they are known for being really reliable, not needing a lot of service. So yeah, I can just show you real quick what I have here. So this is it. They're not small, and what it is, it's basically in the bottom here is a normal 96 well PCR machine that kind of slides into the rack, and it really is another model of that they just, you know, they sell those separately, and so they just put that on a little sliding rack, and took the lid off, and then the top unit here is the optical unit. And if you look in the back here, it's, I don't know if you can see this, but you can kind of see that inside it's basically one unit that's connected to the outside with a little power cable and a serial. And all you need to use it is one of these National Instruments cards and an old computer. So I got this like $20 old computer to run Windows XP, which is all it supports, and like this $80 National Instruments card to talk to it. And so the whole thing cost maybe $400, and oh, maybe it went to sleep. Anyway, yeah, I'll try to show that in a bit. But yeah, this is a single channel model, and it works. And we got a hold of one of the original people who were tech support for these back when they were still being sold, and got the software and got the calibration files and everything, calibration procedures. So this is a totally viable option for someone who wants to have their own PCR machine. And there's also a 2-channel model that exists, and I have one over here, but I haven't figured out how to calibrate it yet. There's some dies I didn't have access to. So that's not, you know, fully open source. It's not open source at all. But we have been working on reverse engineering the protocol. So far, we've reverse engineered the electronics on it. I'll put out a link in a bit. One of my friends, Alex, he did a great job. He actually wrote VHDL to describe the electronics for the optical unit. And we were kind of hoping that maybe we could start by replacing the electronics and then replace one component at a time until we got the full open source, open hardware. Another thing that he did is we don't want to be running Windows XP obviously directly on the metal. It's not safe, it's not secure. So we tried running it in a virtual machine, and again, Alex, he did a great job. He actually got it running inside of qEMU, which requires patching qEMU a bit. So now any modern machine with a PCI slot, you can just load this virtual machine up that we have and start using it as long as you have the PCI card. So that's where I'm at with my hacking efforts, and I wanted to open up the floor to see if anyone else wants to update on what they've been working on.
I don't have much to add here, but I've been on a bit of a similar mission at the Victoria Makerspace with regards to an ABI 7000 that we acquired. It's a similar machine in many ways to the one that Marc's just described, same era, and I think may have a couple of different fluorophores that it can use. Though the one thing I wanted to get thoughts from people about, though, is that I've had a very hard time finding calibration plates that I can use for this. I can still get one from ABI, but they want like $1,500 for a calibration plate. And so I've managed to find Josh at Chai Bio with the Open qPCR has a hex and FAM calibration kit. But I've not found a solution for calibrating any of the other fluorophores that is reasonably inexpensive. Have you found good solutions on calibration kits?
I have a solution, but it's kind of a cheat, but maybe you can use the same cheat. All the people doing COVID-19 diagnostics, they're going through these calibration plates like crazy, and so I happen to work for one, but you can just ask them, because they probably have some that are expired, and for them it matters a lot if they're expired, because if they're expired, they're not allowed to use them for QC purposes. But they probably have some that are expired, and they'll probably give them to you if they're friendly.
That's a great thought.
Yeah. Hex and FAM are also the ones that I've found that are easy to get. So yeah, the other ones are a little more difficult. Also, interestingly, the ABI 7500 is actually actively being used diagnostically by real companies. So it's not like it's too out of date. The 7000 is pretty close. Yeah, anyone who wants to speak up, feel free to do so. Otherwise, I'll keep rambling.
I had a question, and thank you for introducing this concept so far. But do you think that we have to stay with this like type of PCR, qPCR machines, or are there ways to maybe hack together like a single tube qPCR setup?
Yeah, it's a great question. I think. I mean, the short answer is I don't know, but I have seen different solutions that make me very encouraging. I can't remember the name, unfortunately, but I was at, if anyone knows Adeline, who's been to some of these past bio summits, she was working at the Bronx Zoo, and I visited her at her lab, and she had a device there she was working with, which was a portable qPCR setup that was using an iPhone as the sensor. So that was a commercial product.
That's a Philly company.
Sorry?
It's a Philly company, Biomeme. I just put them in there for you.
Oh, cool. Do you know how expensive those are?
10,000.
Okay.
So not cheap.
Yeah, so I assume most of the magic there is in the reagents. Yeah. Yeah, so I know how these things I have work, and they're actually using photomultiplier tubes, which is old-fashioned but also very accurate. That's a way we could make one, a DIY one, but that's probably not going to make it small. Most of the new ones are using CCDs, but the fancier ones are using these silicon photomultiplier CCD things. They're basically arrays of silicon photomultipliers, and you can get them from Hamamatsu, but they're not cheap. Obviously, you know, compared to a qPCR machine, they're cheap. Like they're probably less than $1,000, but yeah, that might be one way to go. Since people are able to do it with just a normal iPhone CCD sensor, then you know I don't see why we shouldn't be able to do something similar. Maybe like an off-the-shelf CCD and a Pelje element to reduce the noise or something like that. But I thought there was a project. I thought there was going to be some people here from this other project that I forget the name of. The one big giant lab or whatever it's called.
Joggle,
yeah. They were working on one, and I was hoping we would have someone here to update us on that. But I guess not.
there are a couple of interesting PCR metafluidics designs, but I haven't seen anybody put a qPCR design up on metafluidics. I really hold out a lot of hope over the longer term for that, though, just because of the miniaturization and lower reagent costs that kind of approach would have with it.
Cool. Oh, I see some. Sorry, I had been missing the stuff in the chat here. So why would a Pelje reduce noise? So noise in CCDs and electronics in general is related to temperature. So usually you can get lower noise by just lowering the temperature on your CCD. And a lot of scientific equipment that uses CCD will have a built-in cooler of some kind. Usually it's a Pelje. Sometimes they go all out and they do some more fancy thing like Sterling cooler. To like some of the stuff you find in the cell phone towers uses actually Sterling coolers to get down to like really like almost cryogenic temperatures. If you want really low noise, you also see that in astronomy equipment sometimes. But you can get somewhere where you can get better performance just with one or two Peltiers. And then there's a link to Fernan, link to a 1-tube qPCR. That's interesting. So 3D printing and milling a real-time PCR device for infectious disease diagnostics. Very cool. I hadn't seen that. Very cool. Well, so
And also Mackenzie would like to know what you feel about LAMP.
oh yeah, yeah. I mean, LAMP is great. My experience with it is that it's something that's hard to DIY. But if anyone has experience with DIYing LAMP solutions, then I'm all ears. That would be great to hear about. For those who don't know about LAMP, it's an isothermal version of PCR where you don't have to cycle the temperatures. And not only is that convenient, it's also usually faster because you can do all the reactions at one time instead of having to wait for one to finish before going to the next step. And that's especially nice for virus diagnostics because the first step is usually the reverse transcription, and that can be a chunk of the time you're waiting. Maybe if it's taking you an hour to do the whole thing, it might be 20-25 minutes of it is the reverse transcription. So if you can do that simultaneously, now you can cut the time. Sometimes you can cut the time down to 10 minutes, 15 minutes for the whole thing. And maybe that is the way to go. Maybe the old school qPCR doesn't make sense, but often LAMP solutions are not as generalizable as qPCR.
You know, Marc, if Free Genes or Open Bioeconomy are working on any of the reagents one would need for LAMP?
I haven't heard of anyone working on it. Yeah, if anyone knows, please speak up. But that's what my hope with this session is that we can get everything that's being worked on out there in one big pile so we can all be in sync. Guy Heidelberg is LAMP whiz. Okay. And then there's a question here. Oh, someone says that Joel has a session tomorrow. That's great. I'm a newbie to this kind of work, i.e. finding old PCRs and making them work. Sounds like a huge amount of technical expertise. Where do you start? Yeah, so it can be. There is some stuff that we did with these things that did require like deep technical knowledge, like getting them working inside of a virtual machine was something that even I didn't want to touch. And luckily we had someone who's like really good at the deep innards of computation there. But just getting out and running was mostly actually not so much about knowing anything. It was more like, oh, these things are cheap on eBay, and then we just followed the thread from there. And there's a lot of searching around, and I ended up like having to hunt down the guy who, like, I found a manual on some university's website that laid out how to use one of these things and how to calibrate it, and it was written by some guys whose name was on there, and I found him on LinkedIn, and it turned out he still worked in the support department of the company that bought the company that used to make them. And so I got him on the phone. It took a while, but it happened, and he sent me all the stuff we needed, and he guided us through it. So, a lot of the time, and I've had this experience with other old lab equipment, is, often people are really excited to help, especially if it's something that, like, they used to work on 20 years ago and they haven't heard about in a long time. If you can find the right person.
Yeah. Be really careful with software on that, though. With some of the old machines, the machine is there, but the control software is just made of unobtainium now.
Yeah, very, very good point. Though sometimes you can get lucky. So what I've done sometimes is I've gone on eBay, and sometimes very often people are silly, and they take the photos of everything, including the serial number. So I will before I buy it, I will contact the company telling them, hey, I'm in this lab, I have this old thing sitting on the shelf, but here's the serial number, we lost the software, can you send me a copy? And usually they do. But it's not always true. I mean, Thermo doesn't usually, but other companies have. I'll give you a little bit more lab tour here. This thing is a pipetting machine. It's a multi-pipetter from Biotech. These things are also super cheap. It's like an 8-well multi-pipetter with 6 SBS locations, and they're like $1,000 on eBay. Of course, no software or nothing, but let me know if you want the software for this model. Yeah, I just contacted them to send me the software. They didn't send me the serial because I didn't have like the license information. Like the software wouldn't start. But that's why we have a local hackerspace. So these things are not hard to crack. Anyone who knows their way around the debugger can easily crack a whole piece of lab software. It probably won't take them more than an hour.
had an interesting experience with an automated microscope that we picked up that had no software and did the same diving down the rabbit hole trying to find it, and didn't find the software, but found the dev lead that had originally built the software that was thrilled that this 20-year-old automated microscope was trying to be used again, and it has been invaluable in helping us.
Very cool. Yeah. Let's see, any questions here? Reclone.org. What's reclone.org? Oh, and for anyone who's like sitting there in a different country, because I used to be in a different country and I used to have this problem, and they're like, yeah, I can't access US eBay because they don't ship internationally and these things are heavy. And feel free to reach out to me or anyone probably in community in the US, or like our hackerspace counterculture labs. Just reach out. We will totally buy it and try to get it to you. If there's something you want that you see on eBay or Craigslist or whatever, just use the network. I know your pain. Reclone.org, Reagent Collaboration Network. All right, I have to look at this. I haven't seen this before. Is there anyone want to talk about Reclone.org?
There was also another question about hardware, and which do you think are the main parts that are more likely to be broken? It was asked.
Oh, the things that's most likely. So actually, one of these I bought it in broken condition, and yeah, let me show you right here what's going on. So a lot of the time, what I care about when I buy hardware is that often I'll buy something without even looking at it if it says won't turn on, if it's biotech hardware. That's the best kind of broken, because usually labs will throw things out if it doesn't turn on anymore and they don't have a service agreement to fix it, because they won't try to fix it themselves. It often is like a fuse or something silly like that. So here, this one won't turn on. That's why I got it for $300. And what happened is, you can see inside here. I don't know if you see that. Maybe not. But on the outside, there is a place where you plug in the power. And the power's not plugged in because inside I had to bypass the outside power jack and plug into the internal unit directly. And that's all I had to do. I literally just had to bypass, open the back latch and plug in directly to the unit instead of plugging into the outside. Fixed. It's like, anyone could have done that. You didn't even use a screwdriver. So, sometimes you take a risk and then you have to sell it for parts or something, and maybe you take a bit of a loss to sell it back, but oftentimes it's really easy.
If you have a university in your town, walk the lab halls if you can too. I have had incredible success with things that are broken in trivial ways being set out in front of the labs for disposal.
Yeah.
Also, Kevin has raised his hand, and I would like to also remind all the participants that you can raise the blue hand, and then you can talk instead of typing your question too. Kevin, would you like to talk about your question?
Yeah, I was gonna, since nobody spoke up about Reclone, I can talk briefly about that, or what I know about it. I know that Jenny Malloy is one of the organizers of that. She was in another panel earlier today, I think, in another track. But either way, it's an interesting, cool project that's kind of taking open source hardware, but into BioWare a bit more. So open source enzymes and figuring out how to make these things available, and so on and so forth. So that might be the right place to start to look for these calibration reagents or whatever, I guess, maybe. I don't know if that was the idea behind that suggestion. Either way, yeah. Maybe a new cool place to hang out. And then I was going to ask another question about, I guess, so yeah, you buy some equipment, you take a loss, maybe you sell it for parts. Sounds like this is something you do on a regular basis almost. Is it I mean, it sounds like fun to some extent, where you sometimes it works and you're lucky and it's super cool, and then sometimes it's just to deal with that, I guess. You just kind of roll with the punches, right? Is it how much, what is failure like when it comes to buying these things? And I don't know if you spend huge amounts of time on each device, or if you get something and you're maybe the software isn't there and they're just all right, forget it, let's sell it. I'm wondering what that's emotionally, yeah. or financially, I guess, too, a bit. It's
a good question. So we have this organization locally that the biocurious and counterculture labs can access, which takes in donations from, very lucky to have this, takes in donations from the biotech industry, and that's where we get a lot of our stuff for free.
Right, I've heard
but,
this, yeah.
But often they don't have the software, but they do have this big box of like random software that they find in their donations. So sometimes I find stuff there, and I really wanted to make like a pirate site for all this ancient lab software because I feel like no one really cares about it, but also I don't know how to do that in a way where it's like not obvious it's me, and like you know, it would be great to have, and maybe we need to talk to the Internet Archive or something. I feel like that might be the right spot to put this, and call it abandonware until proven that that someone cares about it. Yeah. With regards
to collaborate on that.
Oh yeah, great. Yeah, maybe we should talk to Brewster Kale about that. He might be into it. Yeah. So
we have around 5 minutes left.
Okay, so we should
if we still go to a few more questions. One is, what's open enzymes? Could you talk a little bit more about that?
Yeah, who wants to talk about that?
I can talk about it, maybe.
Yeah, if somebody who's actually got involvement with these bio.
So I'm very slightly involved, but basically, cool. They've been going through patents and seeing what's going off patent, and then putting the DNA, and then with the help of free genes, they've been sending out these enzymes out to people. So then basically you can make your own enzymes. These are mostly like polymerases or things that will cut DNA or things like that. And if you have ideas for other enzymes that might be going off patent, you can send them ideas. And then the Reclone network is really, it's kind of built on top of that about how to actually use those. And let me say one other thing, that we were also trying to hack like a qPCR machine, like it was really old and it wasn't really working. But then we got it to work, and then also it wanted like a plate for calibration. And they wanted thousands and thousands of dollars for that, but it was, in the end, we figured out that it was just a plate with like FTSE, with like one color, every single well, the exact same thing. So it's something that cost $1, but Thermo was asking like almost $2,000 for.
Which can you talk more about that? What's this qPCR machine that you got up and running?
It was an ABI 9000 something, like, right, a 20-year-old qPCR machine. Just the software would not work unless it was calibrated. And I found in some document, in something that you could buy from a different company, that it was basically just this plate, that it was all the same thing. I missed the beginning of your talk, so I'm not sure exactly what the question was, but.
Yeah, and that reminds me, we actually bought several of these machines that I was talking about, and when we got a hold of the main support guy who used to do support for these things, he actually, it turns out these calibrations, unless you want like insane precision, they don't actually have to be redone. You can actually just reuse the factory calibration. And it turns out this guy had a library of factory calibrations for these machines. So he was able, for some of our machines, he was able to send us calibration files just based on the serial number. So it really can help to get a hold of the right person at the company.
Mm-hmm.
Yeah, someone asked how we can get in touch with me. You can just, I'm marc@juul, I'll just type it here. And also just, info@counterculturelabs.org.
Thank you, Marc. And also people are commenting that a lot of super cool links were shared on the chat, and we are going to move them to the common document later, so you can all have access. Great. And we still have time, 2 minutes for two. Anyone want to raise their hands? We still can have 2 more questions.
I have a question. It's a little off topic, but Marc, how has the experience been in this COVID world, running counterculture labs? Have you guys been able to, how have you been able to adjust?
Yeah, so we actually did this, we were shut down for a while, but then we did a thing where we opened up for one person to be there at a time, and we made a calendar and a mailing list just for the people who had access. So we made a process whereby you have to apply for like special access and say, why is this important enough? And I think we have like 4 people, including myself, who did that. And schedule so we don't overlap. So there's only one person in the lab. We're talking about maybe increasing it to like 4 or 6 people at the same time now. And mostly it was people who were trying to continue the open insulin project, who got access. And other than that, I think people have just had to adjust. Some people switched to bioinformatics work at home. And myself, I set up this tiny lab here in my yurt, finally getting a space that's not contaminated by air pollutants tomorrow. But yeah, that's been challenging. Can't really do much except like hardware, software work in space like that. Oh. There is a link to something made by Jim Hasselhoff for a hot air PCR lamp. That's very interesting.
Oh, there was a question asking for you to talk a little bit more about open insulin. How is that going? And I would like to take a look on that too. And also have a question for you. And how are the work on the bioreactors for the open insulin? Are you working on that? And do you have anything to share on that matter?
Okay, so I have not been that deeply involved in the open insulin bioreactors. I come through and I see what people work on, so I can't really give an update on that specifically. I know open insulin have what they believe to be pro-insulin at this point in time, and there's been a lot of work in the lab to isolate and verify that it really is pro-insulin. I'm not sure, I won't speak on their behalf on the confidence level of whether or not they have it, but I know they did an immunoassay that was positive recently, which is a good sign. So I think they're, very tiny amounts is where they're at, and they're trying to scale it up. So it's probably, the relevant question is probably, how is the bioreactor going? And I don't know the answer to that. The aspect I've been working on is mostly trying to get a better process for us to verify that we have what we think we have, because this is a thing that a recurring theme in our lab is that people genetically modify some organism, they grow it in small amounts, and then they want to see if it worked, and it's not GFP, so how do you tell if it worked? And it ends up being a lot of running gels, running immunoassays, things that are expensive, things that are slow. Yes. Whereas if you look at something like Ginkgo Bioworks or like people with enough money, then they just have a LC-MS system where they run it through HPLC that feeds straight into a mass spectrometer, and then it tells you what you got. And we don't have that. We don't have a mass spectrometer. We barely have an HPLC system. So trying to figure out ways around that. I've been working a little bit on infrared spectrometry, trying to look at Raman and figuring out how we can hook that in line with an HPLC system.
Yes. Okay. Well, thank you, Marc. I think that now we really hit our time, and I'd like to thank you very much for everything that you share, and also everyone that participated on the chat. There are very cool links and questions, and we are going now to talk about Wearable Biotech with Pat. And is Pat there?
Yes, I'm here.
Yes, Pat. I would like to pass to give you the mic so you can talk a little bit about your work at the MIT with this research. And I have been following your work since last year when I met you at the Bio Summit. It's really cool. So I'll give the word to you.
Thank you so much. Isis, can you see my slide?
Yes, we can see it.
Great. So, I'm Pat, by the way, and I'm really excited to be here and share about my work on wearable biotech, and kind of going in the same theme as the first panel. I mean, the space research is actually really exciting, and we actually, with my community lab in Thailand called Freak Lab, we just sent a project to space, which is kind of on the idea of using DNA as a storage, as a DNA storage for space exploration, to see how microgravity really changed the way that DNA cell assembly work in space. And we have been kind of working with Blue Origin and many partners. So I really encourage people to think about space exploration. It's really exciting. And yeah, one of the things that I really excited about BioSummit every year is that I get to, turn myself into dinosaur and welcome people to the Media Lab. And, I have been doing that for the last 2 years. And, because of COVID, I'm kind of looking forward to next year when maybe I'll turn into a different kind of dinosaur. And as many people know, dinosaur is one of my favorite things. It's, you know, been my favorite subject since I was a kid. And, you know, for me, dinosaur represent the power and the beauty of biological system, you know, the organic growth, the elegance, the complexity, and all the amazing thing about the biological system. But we know that, you know, dinosaurs are all dead, you know, like biological system have limitation. And I think one of the questions that we are thinking a lot about is like, how can we make biology better? So we had a chance to bring back dinosaur. Maybe we could think about the coupling of biological system with some sort of like digital augmentation. We hear a talk about implant earlier and many digital technology that can augment human capability. You know, how do we create a bio-digital symbiosis that could bring the power of bio and digital together? And I used to think of biology as something that, you know, evolve over time, something that is very powerful, very timeless. And, you know, digital system as something that, you know, very fast, very precise, and things that are very timely. I mean, we are living in a digital kind of society right now. So by combining these two things together, we should think about new kind of technology that can emerge, something that could harness the power of being timeless and also being timely. And I just finished my master, and now moving on to PhD at MIT. Thank you. And David is actually one of my thesis reader with George Hurt as well. And my work was actually exploring this intersection of biodigital symbiosis for human augmentation. And, you know, to think about that, in my first chapter, I actually, you know, wrote a comic strip that sort of like highlight what I imagine will happen when biodigital really merge. You know, when human become an interplanetary species, as the first, as our amazing first panel was talking about, you know, how do we create wearable devices that allow us to, you know, thrive in space? As we know, you know, the biological system need to adapt to cope with, you know, the loss of gravity and all kind of extreme conditions for space. How can we produce biological compound from, you know, bioactive compound to pharmaceutical compound, medicine and more on the human body? So when astronauts live in space, they can have access to all these medical and biological compound. Or how do we even thinking about, you know, putting a lab on the body so that we can kind of keep testing different biomarkers that could be the sign of health issues. And this is definitely really relevant right now with the COVID situation. Or even thinking about the way that we can augment our intelligence by kind of having a symbiotic relationship with AI or artificial intelligence. And, you know, kind of all of these combined together, we can think about, you know, the kind of like the future of human life, where we are free from gravity and become the wanderer that travel across universe and searching for the meaning. And, you know, this is just some of the highlight from the comic, but the story is much longer. But, you know, different idea that I kind of talk about what actually based on the project that I was conducting at the MIT Media Lab in my group called Fluid Interface, which, you know, people usually think about it as like liquid water, but fluid mean kind of digital and human fluidly coming together. And one thing that we think a lot about when we think about, you know, putting human and technology together is we think about the closed loop system, where technology can understand the context of the person, from the physiological condition, the behavior, the location, and many more, and be able to provide the right intervention in the time that the person needs them the most. So then when we do this in the closed loop manner, we can augment human capability and create a condition where the body to thrive. And if you zoom in and see the signal that the body is giving out, we see electrophysiological signals. You know, these are EEG from the brain, EMG from the muscle, EDA from the skin. These are electrical signal that we use to communicate and sync different organs together. We also have another type of information that the body is releasing, which is the biochemical signals. These are RNA, protein, change in hormones, enzyme, and any more. These things are very hard to measure in real time, but are very exciting to look into as well. Current wearable technology today only tap into the electrophysiological signals. Your Apple Watch or Fitbit will be able to measure your heart rate, but not really your gene expression level, right? Or the change of hormone and many more. So there's a lot of opportunity to think about how can we create the future of device that can kind of tap into this information. And that's all like become the theme of my research during my master year at a media lab, which is looking at the wearable that can sense the biochemical signal and also provide the right intervention. And that is expressed in two projects. One, we call it Wearable Lab, and another one called Wearable Bio Reactor. For the Wearable Lab project, we asked, what if in the future you can have a lab on your body? And this project, we are currently working on it with NASA, TRISH, which is an institute that focuses on the space health. And you know, the name kind of suggests that we want to take the process that are usually done in the laboratory and see if we can find a way to miniaturize or put it on the human body. And you know, with COVID, you know, many people, including myself, need to go have a test, you know, every couple week or every couple day, and we sample our biofluid to see if there's a biomarkers that are the signal of COVID or other type of biomarkers that could be the indication of our health issue. One of the biofluid that is very popular amongst medical practitioner to use is the saliva, because unlike blood, you can kind of sample the saliva non-invasively. And saliva has many biomarkers that are similar to the blood, but in the lower concentration. You can look for electrolyte, hormone, enzyme, and many more. And people have been using saliva for measuring and monitoring conditions like depression, fatigue, health failure, and many more. So we made a prototype that is essentially a device that continuously samples your saliva and places on a rolling strip of biosensor. And these biosensor are kind of like the dipstick that we use, you know, for monitoring different biomarkers in urine. But and they are one-time use, so the device need to be able to kind of constantly rotating and switching to get a new readout. And you can imagine that in the future, these paper strip can be like a COVID test or all kind of tests that you can input into the system. And what we made is essentially a platform that can allow different biomarker researchers to install new sensor in it. Similar to how your phone can have limited capability by installing new app, our wearable device serve as sort of like the interface between the body and the sensor. So we constantly sample the saliva for you, and you can install different sensor to see what you want to sense. And these are some of the kind of chemical that we were creating the model for in order to get the readout of the body biofluid. And because the device sits on your mouth, you can also get the accelerometer information to understand the context. Like when the person is drinking, eating, or doing different things, you can use that to contextualize. For example, you see a high spike in glucose, and you see that the person is eating something, you might make a hypothesis that that signal comes from the food intake, not from the body signal. And you know, if you can kind of combine this biochemical signal with other form of information that we already collecting from our wearable device, like heart rate and EDA and many more, we can create a more preventative approach for medicine in the future. And now that we sent the information from the body, how do we intervene in the time that is the most needed? And you know, we asked another interesting question: what if we can produce kind of medical compound or bioactive compound on the human body? And this is also a project that we are working with NASA, TRISH right now. And one of the inspiration for this project was, you know, something that is we are doing every day. You know, for a human life, we kind of take different kind of biochemical intervention, from drinking coffee, getting caffeine, to serotonin before going to sleep, or you know, taking medicine when we are sick. Right? These are molecules that our biological organ cannot produce, or produce in the sufficient concentration when we need them the most. So what if in the future we have a programmable organ, a new type of organ that we can program to produce things that we need in the time that we need them? And you know, these can also be getting information from the sensor that are kind of constantly checking our health information. And currently, you know, many researchers, both in the academia and in the community lab, like or we just talk about the Open Insulin Project, are thinking about hacking the living system to produce bioactive compound, right? Right now we are kind of producing them in large quantity for mass kind of distribution. What if in the future there's another way that we can kind of produce them just for the person? So personalized fabrication on the human body in the wearable device. That's kind of one vision that we are exploring. And people have been miniaturizing people have been miniaturizing bioreactor for different applications, from on-demand bioreactor for that can be installed in the ambulance car, to cell-free system that you can use in the field, and even some high fidelity biodigital conversion that can produce pretty much all kind of bio compound, which require your robotic arm and multiple modules. And the list of biomolecules that people are producing also keep expanding over the year. And I think recently people are very excited about producing psychedelic compound using yeast, right? So that could be really interesting. Also, there's an emerging area of research on on-body biological interface as well, from the work in the Media Lab by Neri Oxman group to Hiroshi group that focus on printing bacteria cell on textile, to even creating a patch that allow the cell to grow on the skin. But finally, I think the most important area that we need to also consider is the way that we can make biosystem talk to the digital system. Otherwise, the cell will just gonna continue to grow and do its own thing. How do we synchronize the living cell that we install on the human body with the human body itself? So many research have been looking into the way to create a biodigital interface, from using optogenetic approach, using light to turn on and off gene, to using electrogenetic approach, where we use different kind of current to actually trigger gene expression. And by combining these three areas together, we see a really interesting area where we can think about wearable device that produce biological active compound for personalized use with digital control. And that's what we did. This is a project called Wearable Bio Reactor, as I said, and we kind of thinking of it as a programmable cellular manufacturing on the human body. And it's a work in progress where we use the genetic circuit developed by our collaborator that not only allow the cell to see the light and be able to use that to turn on and off gene expression. This circuit can allow the cell to see more than one light and be able to switch gene expression based on the wavelength that is being exposed to. So you can think of this as having a cell execute 3 different commands based on the light signal. And the team have a beautiful demonstration where they make a petri dish with this circuit inside the cell. And when you project different image on it, the cell that were exposed to the green light will produce green pigment. The one that exposed to the blue will produce the blue pigment, and so on. And they have a beautiful bio painting, as you see here. And we have been kind of hacking this circuit and change the output so that we can kind of produce molecule that we kind of interested in. And from our experiment, even though we see some kind of leakage in the system, we'll be able to kind of get the corresponding protein based on the wavelength that we give it to the system. And imagine that in the future, unlike how the body produces all kind of hormone and enzyme, if we have a device that become our programmable organ, we can think about allowing human to produce different molecule in the right time and in the right condition to prevent overdosing and relying on external source of bioactive compound. So empowering human to become an augmented human. And we can see this, for different application, like, how do you become more alert by maybe program your body to produce a little bit of caffeine in the morning, or a little bit of psychedelic compound to become more creative, or some molecule that can help people stay alive in space. And this, we think, really pushed the concept of synthetic biology to the idea of biodigital interface. And to host these, this genetic circuit, we have been looking at the way that we can print different kind of microfluidic device that can host this cell and we have been characterizing them to show that with the 3D printed microfluidic, we can also grow the cell and also have them produce the compound that we are interested in producing. And bringing that all together, we are prototyping a wearable device for astronaut so that they can have a wearable bioreactor on their body. And kind of inspired by this picture of astronaut, we really like the interface on the arm, which is kind of really futuristic and also really useful. And by bringing the idea of bioreactor together with the sensor and the molecular delivery system, which has been explored by many research groups, we kind of think about the closed loop health enhancement that can have impact beyond astronaut health to everyday people in the far future. And yeah, so this is what we think a lot about biodigital augmentation, and these are amazing people that I have a chance of working with. After we work on this project, we also kind of think about the way that this field can kind of move forward in the future. We have a theoretical concept called living bit. Right now we have digital bit, where digital information is used in computational system. What if in the future we can integrate digital bit with living bits, create a continuation of computation from digital to biological? And we have surveyed many works. Actually, some of them are from our community as well, that have been exploring the intersection of biodigital coming together. And right now the paper is published. If you're interested, you can take a look. And we have been kind of characterized different area where people bring bio and digital together, from embodying information to communicate signal that are usually lost, which is purely digital system, materialize new ability, and enhance existing capability, and even something really playful, like create a biodigital game. And this thing can happen across scale as well. Finally, I will share my last two projects very quickly. Beyond expressing the controlling the gene expression, thinking about human and biological system at the DNA level, we also think a lot about how human and intelligent system like AI can become our second brain and augment our cognitive capability. What if in the future the AI will help us by becoming our second brain, not just the tool that we use? And we had a project called Wearable Reasoner, where we think about the world full with fake news and malicious information. How can we train an AI that we will have on our body to kind of help us become more rational, help us distinguish between fake news and news that are trustable? And from our experiment, where we train the AI on recognizing information that is kind of reasonable and information that is not reasonable, we can kind of enhance kind of human thinking capability from the experiment that we did. Not only that, digital and biology is becoming closer to one another, we also seeing a new type of digital information that are emerging, the type of digital information that really mirror the complexity of biological system. This is a project where we use AI to become my twin. So this project was inspired by a film Godzilla, after I see that there's a monster in Godzilla where we have three-headed dragon. What if in the future human can also have more than one head? Some head would be biological and another could be augmented by digital technology. And this will allow us to maybe have a conversation with different version of ourselves. In this case, I train the AI that become my second and the third head to be, a different a version of myself, a more masculine, a more feminine, a younger, an older version of Pat, and allow me to kind of ask questions and talk to sort of a different version of myself. And bringing all of this together, I really believe that in the future, not only that we will live in more society that become more digital, but we will see kind of a seamless connection between bio and digital technology coming together. And as I said, the power of biology is very timeless. The power of digital is very timely. By putting all of this together, we can create a symbiosis system. And that was the term that I used in the title of my presentation, Homo symbioticus, which signifying the human species, not just Homo sapien, the people that make tools, but people that make organs. And we can have symbiotic relationship with this organ that we create. And human will become a symbiotic being. So with that, I'm really excited to have a conversation with all of you about this topic, and really believe that the community that we have here will really gonna do amazing and wonderful things together if we kind of be futuristic and think beyond what the world is happening right now. And with that, I will end with another dinosaur. So thank you very much.
Thank you, Pat. That was incredible. And now we still have some time, 5 minutes for questions. Anyone would like to raise the blue hand and talk to Pat? You can, we can have your microphone open. Oh, okay. Eugene?
Hi, Pat.
Hi.
How would you go about producing things on this 3D organ?
Yeah.
On this, sorry, not 3D organ, wearable organ for the astronauts.
Yeah, so right now we're growing cell in a liquid culture. So the cell will be kind of suspending in a wearable microfluidic device, similar to when we grow them in a bioreactor. But as they're growing, we will kind of use the light to signify what we want them to produce and control the gene expression using the circuit that I talk about. Yeah.
So right now there's 3 different light systems, right? Would that correlate to 3 different kinds of compounds it can produce?
Yeah,
or
exactly.
How would you expand it out to be more different things? Like
Yeah.
could one of these be build a benzene ring, then add a phenol group or add a different group or something?
Yeah, I think that could be definitely a really interesting option. I think the limitation right now is the photoreceptor. The photoreceptor that in biological system are not like the light sensor that we use in digital system, right? There are a lot of overlapping, and the reason that right now we can do 3 different wavelengths because these receptor have sort of like a distinct wavelength that excite the system the most. So in the future, I think we can imagine engineering the protein that become the receptor to be very narrow. So we can have like maybe different type or many more type of receptors on the surface of the cell. So we can maybe execute like 10 or 100 of genes using light or other form of digital signal that can kind of, control the cell expression. Yeah. But that's a really good question. There's one paper that came out, I think, recently, where they coupled the protein with the photoreceptor, and I think they were able to do 7 wavelengths. So you can trigger 7 enzyme. They're not doing at the transcription level, but at the enzymatic activity level, where they can have the cell, have 7 enzyme activate at different time based on the light that you shine on the system. Yeah.
Pat, I have a question.
Yes.
Well, first, I just wanted to say that was amazing. Your thesis was incredible, and your work is really sensational. I'm sorry, I apologize if I missed this, if you spoke about this, but did you mention the event that you organized, the Wearable Biotech event?
I did not mention that. Yeah.
Well, I just want to comment for everybody. Pat, I think in addition to this really remarkable research, is really trying to launch a discipline. He's really trying to define a new type of a research area, a new multidisciplinary research area. So, Pat, I think it'd be really interesting for you to talk a little bit about the workshop that you organized and your vision for what wearable biotech might be potentially as a type of research area.
Yeah, so as I said, I'm particularly interested in the interface of digital and biological system coming together. Especially as I said, there are a lot of things that that digital system can benefit from living system, and many things that living system can learn from digital system. So and I think we are at the surface of that right now. I mean, the field is very young, and it's really exciting to see many people that are actually doing this kind of work, not just in the university, but in the community lab. Like many of the projects that I talk about in the Living Bit paper are actually coming from people that are in our community that work on like biodigital game and so on. So I think, yeah, I guess my future vision would be kind of on this area of biodigital interface. Yeah.
Maybe just one other thing to add, Pat. I do think, though, that the fact that you organized this particular workshop is a very powerful thing that you did, because I think it's one thing for people to be developing individual projects in an area to say, hey, I developed a cool interface, this interfaces with my body, et cetera. It's another thing to try to articulate a coherent narrative for how a whole bunch of different pieces of work that people may think is one thing, but then you're providing a metaphorical framework and a conceptual framework so that people can understand how their work fits into a larger narrative. And so I think that was the power of what you did with this workshop, so that now other people can say, oh, wow, I think my work is actually part of Wearable Biotech. This is actually, my work actually fits within this larger context that you have helped to frame and also organize a community around, which is, in a way, is also part of what the BioSummit is. So anyways, I just want to commend you on that. And I think, hopefully you continue to do that work and pull in others, both from this session here and beyond.
Thank you. And, I was really inspired by the BioSummit, and, I came to the media for the first time because of BioSummit, because of, David and the community. So it was really awesome to, continue to be part of this, and, looking forward to become another type of dinosaur next year when we get to welcome people back at the Media Lab. Yeah. I think maybe that's the essence of wearable biotech, become a dinosaur. Yeah.
Somebody make a poster, somebody make that t-shirt.
Yes. Yes, that should be the star and the mighty star. Well, but we still have 1 minute. Would you like to wrap it up with something, any additional comment, or would you like to open to a new question?
I'm reading the comment in the chat. It's really cool. Yeah. Yeah, and if anyone have any question or thought or idea to collaborate, you can always message me on Facebook, on email, or I'm kind of in the community, so please feel free to do so.
Oh, and also, for those of you that did not know, this beautiful logo behind me is Pat's design.
Oh.
Pat has designed the BioSummit logo every year except for the first year. And each year it's like, I'm going to lean this way. Like, look at this thing. There's so much going, you can spend like a whole afternoon just like looking at the logo and just trying to understand all of the little things that he put in there in detail. It's so gorgeous. Pat is basically one of the finest designers I've ever had a chance to work with. So he's just, yeah, so skilled on so many different levels. And yeah, we're lucky as a community to have him.
Thank you, David.
Amazing. Thank you, guys. Whoa, that was awesome. We are so lucky. So many amazing speakers. I'm really excited that it's impossible not to attend to a session like this and not to end up leaving like fan of everybody. Like, I'm fan of all of them already. I will follow all of you. And now we'll have a small break of 15 minutes. And then after the break, we'll come back with another breakout session and later in lightning talks.